Hey, what's up, everyone? So, this is my second video for this weekend. Um, today we're going to repurpose the transformer code into a vision transformer. And we're going to train it on the MNIST dataset first, and then we're going to train it and test it on CFAR 10. So, yeah, I guess let's get started. Oh, one thing I wanted to mention, there was a big mistake in my last video. Well, small, but we'll make a big, it's just not correct in layer norm. So basically in the layer norm file that I was using in the last video, um, my layer norm, this is supposed to be here. You're subtracting the mean and dividing by the variance, the square root of the variance, right? I just had x there. I didn't have x underscore var. So yeah, even though it was still working, um, which I'm not sure why. I haven't thought about it yet. Um, I don't really care to. It's just I know that that's wrong. So um, yeah, I'm sure that will cause some issues in the future if it hasn't already. So we're gonna take this code right here and we're gonna try to repurpose it for a vision transformer. One thing that I can tell you already, this attention head will have to remove the upper triangular matrix and the masked fill because it's going to be just attention, not causal self-attention. So it can look at tokens it can look at patch tokens or patches or tokens. We use those words interchangeably in Vision Transformer. So the patches are the tokens, but we can look at patch embeddings from the future and from the past. So anyways, we'll keep this open on the side. Um, actually, let's just do this right now. Causal, we'll call this a causal attention head, and we'll copy this, remove that. Remove that would fail anyways because we're not gonna have this see the context window size. That should be it. Remove these comments. There's a mosquito in here and it's gonna drive me nuts. I think this should actually be head size. Because D, it would be D, the size of the embedding, the token embedding or the patch embedding if it was a single head, but since it's multiple heads, we divide it into the number, we divide by the number of heads. So for a single head, it's going to be of size n embed divided by the number of heads, which is, in this case, is D. When you get x dot shape, D equals head size. Actually, yeah, okay. So we're good. D equals head size. Yeah. Yeah. D equals head size. Or wait. No, it doesn't. It does not equal head size. D equals um, yeah, D is just D. And so we need to say yeah, that's right. We need to do that. So, okay. Wait. Causal attention, head. This is attention, head. And this is causal attention head. Okay, cool. I think that's all we need. And then remember, the layer norm needs to be X-var here. I think we can use this. Let's see those comments there. Okay, so let's start editing this. Let's call this. Mvim bit.py. Am I in the camera? Yes. Boom, boom. Move this over. So let's do some imports. I always try to memorize these. Import torch vision from TQDM. Import TQDM from data classes. Import data class device equals CUDA if torch.CUDA.is available, else CPU torch.manual C1337 import torch.nnfnn import torch.torchvision.transforms as T transforms import torch.nn.functional as F import torch.util.data from import data loader. We're going to work with some toy data sets. Random split from torch vision.data sets import MNIST 10. Let's see if this compiles. If name I already made my, this is a new repo for Vision Transformer. I already made my requirements file, so all those details will be in the description for this video. I already activated my Conda environment, so VIT, any errors, torch. Torch util data util. It's one of those. Oh. Torch data. Huh? One of these. It's gonna be one of these. Cool. So test test modules. Maybe I'll use this. Config. Is that rain I hear? By the way, again, I want to apologize that I don't have my iPad and that the sound quality is so low. Hopefully I can amplify it when I'm editing the video. This is not my ideal setup. I left all my equipment at home at home in LA. It's raining now, which I hope doesn't mute the sound quality at all, but I'm going to continue with this video. Yeah, when I have my iPad, I'll be able to explain these PyTorch operations much, much better. Sorry if they go over your head in this first pass. If I have to redo these videos, I will, but I committed to launching videos when I got here, and I'm just sticking with the commitment, just pushing out an MVP, minimum viable product, keep it moving. I don't want to be a talker, you know what I mean? Just I have this idea, I'm going to get it out. I'm going to make sure like I manifest, like actualize these ideas instead of just talking about them all the times. So, um, you're getting the MVP. Hopefully, you take something from it. So, test modules. Let's pass for now. Maybe we won't need to do that, but I'll put that there. So, for the vision transformer, the big difference is we need patch embeddings. So this is what I would like to have my iPad to explain, but essentially if you have an image, you're going to divide it into patches. So if you're, let's say the height and the width is the same, it's 32. Image size and 32. We're not going to have a different height and width. We're just going to keep them the same. And then you have a patch size. 32 divided by 4 is 8. So 8 row. So divide the height and the width by 4 and then multiply that together. So 8 times 8 is 32. That's 32 patches. So essentially is your patches are considered your tokens, right? So just like you have a sequence for when you want to learn language modeling, you have a sequence of tokens that you feed into your language model. You're going to essentially tokenize your image by making patches of pixels. So we'll say the patch size is 4 pixels, so you have a 4 by 4 patch, and you have 16 of those, and then you're going to flatten them. So you're going to have one long 16, one long vector of length 16, which is your flattened image, and then at each part you're going to have a patch embedding, a patch vector. So you're going to send the pixels of that patch through a neural network, and it's going to project those pixels into another dimensional space, which is your patch embedding. That's going to contain information about that patch. And if you have 3 channels, it's going to contain the information of all 3 channels. So essentially what you're going to do is we're going to, before we can use this transformer before we can use this transformer for images, we're going to need to create patch embedding. So I'm going to create this patch embedding class that essentially creates a patch embedding out of your image. Once we have that, we essentially have what we need. Then we need a class token. A class token is going to essentially contain the aggregated information from the transformer forward passes. It's going to contain the aggregated learnings from the transformer. So the class token is essentially an additional embedding concatenated to the beginning of your patch embedding. So you have your patch embedding of length 16, where let's say the embedding dimension is 32. So you have 32 dimensional embeddings at each 16 of the 16 spots, and then you prepend a 32 dimensional class token or a class embedding. Let's just call it a class embedding. So your image is going to be now represented by a tensor of 17 by 32, no longer 16 by 32, but 17 by 32. And that's going to basically say what class your image is. So if we're classifying MNIST data, which has 10 classes, we're actually going to look at that class token to determine what the class of the image is. We're going to we're going to compare the labels we're going to compare the class token to the labels. and that's how we're gonna back propagate our loss based on the difference between the class token and the labels. So yeah, let's get into it. So let's create patch embedding. It's really good to implement these things from scratch because you really start to understand how to manipulate tensors. And if you want to create things in machine learning, you want to create your own things, right? You need to implement a lot of these foundational models from scratch, and you'll really start to understand intuitively how to manipulate tensors and how to extract information from them and how to extract learnings or create different architectures that learn different things. I didn't start getting a feel for this until I started implementing these models from scratch. So yeah, let's module. I'm gonna pass this config file around again. Super patch embedding contains a linear. It's gonna be to. Again, I like to use hopefully you all can still hear me. I'll speak a little bit louder since it's starting to rain. So C is equal to let's do MNIST first. So it'll be one channel. C equals config dot image. Right, so the image size divided by the patch size. So if the image size is 32, the patch size is 4. That's going to be 8 patches. And then if the height and the width are the same, it's going to be 8 for height, 8 for width. 8 times 8, right? 8 times 8 is 64 times the number of channels, 1 in this case. Because if it was 3, you'll see how we do the unfold operation. We basically flatten the 3 channels into one dimension. So we take a pixel 4x4, and then we flatten it, and then we also concatenate. We basically stack on top of them the other channels, and we send all 3 channels through a neural network at once, right? But channels are 1 in this case for MNIST. So, but yeah, okay. So I think that's all I need for. Is that all I need? We'll see. Let's just keep going. So let's start with the forward operation. So again, I get my shape. I usually get create singular variable names for the shape. So batch C channel. I don't need CN. When we're implementing convolutions, we'll do CN and C out, but C is just going to be for CN channels in. Height, width. Height is always first. X dot shape. Okay. So now we're going to do this unfold operation. Unfold. There are two different unfolds. There's F. There's torch.nn.functional unfold. We'll use that unfold for convolutions when we implement convolutional neural networks, which we're going to do next in the next video. But for this one, we're going to use the unfold directly on the tensor. So x.unfold. So we're going to unfold the height dimension, so 2, and then give it the patch. The unfold takes the dimension to unfold, and then the patch shape so it knows how to the size of the patches to extract. And then I'll do this twice to show you how it unfolds. So this is going to create a tensor of size b c h divided by p w. This is really where I want my iPad, because it'll really make sense what's happening. But I'll just explain it via the shapes here, and then maybe you can look into it a little bit on your own. And then I'm going to unfold 0, 1, 2, 3, this patch dimension, okay? And that's gonna make a tensor of shape B, C, H, P, W, P, WP, yeah, P. Then we need to permute the dimensions and call contiguous to, because what we want to end up with is a tensor of shape. We want shape B, N, C, P, where N is HP times W divided by P. Okay. So to get there, we need to reorder these. To get there, we need to reorder. We need to bring C to the front. We need to bring C right over here before we can call view, because view will only allow you to multiply certain dimensions together that are contiguous in memory. So we need to make C contiguous. We need to make the C dimension contiguous with P and P in memory. So we're gonna do x.permute. So we're gonna take, so this is the 0 index, 1, 2, 3, 4, and then 5, right? We're gonna permute. So what we want is in this order: 0, skip the C dimension, which is 1, 2, 3, and then put the C dimension 1, 4, 5, and then call dot contiguous. And then we're gonna say x receives x dot view. Now we can call view. So this gives us B, H, P, W, P, C, P, P. And what we want is this here, right? So we're gonna say view. Can I do -1? I could just put B there. I mean, B, -1, C, I have C, P equals config self patch size. I like having these singular P. This should give us Boom. This should automatically multiply. It infers that the two remaining dimensions, h divided by p and w divided by p, they have to be multiplied here. It's the only way that that's the only way we could get a tensor. So, and the reason we do that is because, you know, I don't know, it's just easier than calculating h divided by p and w divided by p. So now we say x receives self.project x, right? Because now that this is the dimension that the linear model is expecting here, and it's going to return, right? Now we have b and embed. Now we have a batch of for our batch of images, each image will be n patches of n embed dimensions. So like the example I gave before, if patch size is 4, image is 32, that's 8 times 8 is 64 patches, and 32, so 64 by 32 tensor, and then you'll have b of those for the batches. So now that we have patch embeddings, let's create our vision transformer. And then we'll import, I like sort of import transform modules. Some things are so hard for me to type. We're going to import this file right here. And it's raining a bit harder, so I'll talk louder. And we will use attention head instead of causal attention head, because we're not doing autoregressive language modeling anymore. We're treating an image as a self-contained thing to be classified. So each of the patches should be aware of every other patch in order to determine what the class is. Config, super. Uh-oh, I really hope you guys can hear me. See, I'm talking and I'm looking at where the bar is going relative to what it sounds like when it's raining, and I'm being quiet. And it looks like I'm speaking at decibels, like significantly above what the rain is. So I'll keep going. It actually helps me because I like white noise a lot. I think ideally my ideal setup will be, it's getting louder. I'll have headphones on that have like binaural beats, and maybe I should pause it. No, let's keep going. I'm already here. We already here, y'all. Let's keep going. So, super init. I like to add spaces before these returns. I don't know why, it just logical chunks, like it just feels good to have a space before a return. It's like a logical break. So our vision transformer is going to have self.patch embedding receives patch embedding config. Actually, let's just run this. Okay, this is way too loud. I'm gonna pause the video. Alright, looks like the rain calmed down a little, so alright, we have our patch and I wanted to see if this is gonna run. If there are any, at least syntax errors. 22. Oh, yep. All right, I'm gonna pause it again. So I'm gonna start up again. Just try to project my voice. So I'm gonna start up again. Just try to project my voice. So okay, we have the patch embeddings, and then we need self dot position. We need a class token first. It's gonna be torch dot, or it's gonna be parameters, right? It's gonna be a learnable parameter. It's gonna be a learnable vector of size n embed with number of dimensions equal to n embed up here, right? That we're going to concatenate to our patch embedding, and we're gonna initialize it by pulling values from normal distribution, and it's gonna be of dimension of shape one, one for the batch, one for the token size, and n embed for its last dimension, and then we're going to multiply that by 0.01 or 0.02, right, to scale the initialization values from the normal distribution. And this class token, so this is a shareable, right? So batch is 1. So that means this is a shareable token. We're going to share this. It's a shareable parameter. We're going to concatenate this parameter. We're going to concatenate this parameter to each value, to each sample in the batch, right? So we're not gonna have duplicate parameters. It's gonna be a shared parameter it's gonna be a shared learnable class token for each data point in the batch. And this position embedding is gonna be a parameter, and we're gonna match the shape of the patch embedding concatenated with the class token. So again, we're gonna sample from a normal distribution. Yeah, this is a shared parameter as well. So right. So these are shared positional embeddings as well, across the batch. So this is 1, and then let's call this D. Um, and then let's call n equals config.image size divided by integer division config.patch size squared. So like 8 patches times 8 patches, that's patch embedding of size 64, right? And this is going to be D here, and this is n plus 1, because we're going to concatenate the class token before we add the positional embeddings, and size D. And then we're also going to scale the initial weight values for this. And then transformer module that we imported from over here, we're going to actually, I do need to modify this, I think, because I want to make sure that multi-attention head calls attention head, not causal. Yes, it does. It calls attention head and not causal attention head. Ideally, I'd pass the class in here. I'd pass it in here. And then we could specify it in, when we instantiate transformer or transformer block, what type of transformer block do we want? Like here, causal transformer block or non-causal. But anyways, I'm just going to hard code it in here, attention head, which maps to a non-causal, right? We've removed the masked fill. So and channels and blocks int, let's just say 2. Transformer blocks. Transformer blocks. What am I doing? Transformer module dot sequential transformer block config for in range config.n blocks. Okay, and then head linear. It's going to take in config.n embed and map it to config.n classes. And actually in the Vision Transformer paper, there's a layer norm before. Is there dropout? I don't know. I don't think there is. I don't think there's dropout. No, that's all. That's already been taken care of in the transformer model. Let me make sure I have all the dropouts. There's a dropout, causal attention head after the softmax. There's a dropout in the feed forward. And there's a dropout. Is there another dropout in the multi-head attention? There should be 3 dropouts. Yeah, I think there's a dropout layer here, actually. So this is another mistake. I'll need to make sure I edit the videos, and it's another oversight. And then pretty sure, yeah, there's a dropout here. So where was I? Okay, so now for the forward pass, we do self dot, so patches receives, so first b c width height equals x dot shape, patch embedding x, so this gives us b n d actually we can get, so it gives us bnd, and we can get the shape from patches if we need to, and then we have the class token. So X receives patches, so torch.cat self.class token.expand be -1, -1. Let me actually class tokens. So this is going to essentially broadcast, duplicate your class token. It's going to create a tensor of a shape, or it's going to create like a broadcast token where B is the broadcast dimension, and the other two dimensions are going to remain the same. So we're going to concatenate that to each element in the batch, to each patch embedding in the batch on the first dimension. We're going to prepend it on the end dimension, the patch dimension. And then we're going to say x plus pos emb, okay? Because this should now be shape b n plus 1 d. And this is, again, shape b n plus 1 d, because pos embedding is of shape b n plus 1 d. And now we can say self.transformer blocks x. So now we send it through the transformer, and then we send it through the layer norm. Wait, the patch embedding needs to be, the patch embedding is of shape 1, n plus 1d. So we need to do x and then all, right? So this is going to broadcast the position embedding as well to each element in the batch for x dot size 0 . So this operation, when we add it, since the dimension here is actually the batch dimension for the pos embedding is 1, it's going to know, PyTorch is going to know to broadcast, and then we're going to select from the beginning of the patch dimension up to the size, up to n plus 1, and this is just in case we feed in an image, like we infer on an image that's of greater size, we'll need to limit that to the size that it was. We'll need to limit the patch dimension to the size that it was trained on. And then we want to take all batches and then only the class token from each, and then all dimensions of that class token, right? We're going to call layer norm over that because we don't need to normalize the rest of the values of x. And then we're going to get the logits. Okay, now let's see. So we have no syntax errors. So let's create our training loop. Am I still on the camera? Where am I? Okay. Fortunately, it's not as hot as it is in the daytime. We haven't called test modules yet. That's fine. Train test model. Okay, data set. Data set is going to be MNIST root. I think it's just, I already downloaded it. I think it's like 2 levels. It's a level above. So I'm going to put download false. If you haven't downloaded, this is your first time, you're going to make this true. Transform. This is our transformation pipeline. So it's basically, and it's lazy. So basically when we get a batch from the data loader, on the get batch call, it's going to apply this transformation pipeline, so this is a composition function. So we're going to compose a bunch of different transformations together. And we're going to say first t dot resize. There's a bunch you can do. I'm only going to do a few. So tuple. Let's make sure I'm still in the camera. Config.image size. Config.image size. And then t.2 tensor. We have to turn them to tensors. And then we're going to normalize. Always normalize your images. This is for training stability, gradient, stability during back propagation, certain activation functions. So what this is going to do is it's going to standardize your pixels. So pixels are naturally between 0 and 1, but this is going to make them between -1 and 1, which has a lot of nice properties, like I mentioned. Also, there's certain activation functions that really like the -1 and 1 sort of saturation of those values, like the ability to be in that range, like on 10H. Fig.normalize shape. So first parameters for the mean, second is for the variance, and normalized shape is 0.5. So if you subtract 0.5 and divide by the square root of 0.5, you're going to put your pixels between -1 and 1. So just a standard normal distribution. Let's see if this works. Oh, somehow I indented all of that. I untabbed all of that. Okay, that works. So, what do we do now? We need train split. We need to create our data loaders. Random split. Data set. Train split int minus train split train. That's going to be our train test data. So we'll use the random split function we imported. Call this P train split. that should be good. Train, data loader, train, shuffle equals true. Train, batch, size, config.batch. Man, I'm getting hungry. We're not gonna shuffle the validation data set. I'm getting hungry. Okay. That is wrong. Boom. Okay. Let's initialize our model. Ooh, did we? I'm thinking if I missed some device stuff. Model is vit config.to device optimizer torch.optim atom w model.parameters learning rate 1e -3. I made this -5 once on accident, and it really changes. I mean, it makes a big difference. You're talking about order of magnitude of, thousands of on the order of magnitude in the thousands of difference, right? Which will really change the rate at which you descend the slope of the loss function. So let's just compile this or run this, see if it interprets without any data is not defined, line 93, boom. Data set, data set, boom. Let's see. Torch NN parameter 58. Wait, which file is this in? Vision Transformer Practice 58. I do this every time I type parameter. I literally miss this E like 60% of the time. And heads and heads, let's just say 2. P dropout. And classes. Okay, no syntax errors at least. Optimizer criterion equals cross entropy loss. What else? For epic in range 1 and config.n epics plus 1 tqdm.write. Let's use tqdm right away and just with tqdm, I'm going to say for inputs labels in pbar, right? I'll fill this in. I think it's like description, unit, we'll calculate the loss, we'll calculate the accuracy, we'll calculate the total. Wait, do I put that here? I'm getting turned around. Let's see. We'll keep going. Model train. Inputs, logits, optimizer. Still in the camera. Let's see. Optimizer.0 grad logits. Loss receives criterion logits labels. Loss dot backward. Optimizer dot step. Plus loss dot item times inputs size 0. So we're going to get the average loss by just multiplying the loss times yes, and then logits predicted equals, we'll say torch.max logits over the over the first, over dimension 1. Let's call this, so we're not going to calculate the accuracy yet. We're going to say train correct. So where the predicted equals the label, we're going to sum up all of those ones, and that will give us the total correct in this training and for this batch. And then total train correct train. Yeah, I think this looks about right. Let's just give it a whirl. And epics Hmm. $111. Four inputs. SP bar. Oh, I think with TQDM, I need to give it train data loader. I don't know if I have to call a parameter 43. Self.config equals config. Am I using MNIST? Number channel should be 1, okay. Line 125, linear module, line 50 and forward. Shapes cannot be multiplied. 2046, 64, 32. $20.48. So I found the issue. I don't know why I did this, but P, it was supposed to be patch size, and C is supposed to be number of channels. Yeah, weird. The H divided by P down here would be the image size divided by the number, by the patch size, like I had it. But this is just number of channels and patch size. So this should work right here. So this should work right here. Okay, line 73. Did mean B. Class tokens. Line 52. Transformer blocks. Saying head size is not defined. Line 52. Transformer modules. Oh, right. This is self.head size. 119. Looks like the loss is moving down appropriately. Let's add in the validation. Train. That's it. We should have pretty good prediction accuracy after the first epic, 80 or 90%. If we do, we can just stop this video here, and then the next video will be switching it out for CFAR 10, which won't have nearly, it's a much more complex data set and won't have nearly as good prediction accuracy after even just a few epics. And this will get us into an interesting conversation about vision transformers versus convolutional neural networks like ResNet and inductive bias, and implementing some things. I didn't print. I am so hungry. training is taking a bit long, actually. Batch size 32, image size, patch size, and heads, and blocks. We could have made it one block. Could have made it one block. Oh, okay. Alright, something's not right. Wow, the number of blocks really makes a big difference. Nice. Validation accuracy. Let's see what happens after the second iteration. This looks okay. I really feel like we should see 90% I feel like we should see 90% accuracy very soon. Yeah, this looks reasonable. This looks reasonable. This looks reasonable for MNIST. Yeah, so there we go. We repurposed our transformer for vision. Look at that. It's not mystical. Demystifying it. It is hard. Learning this stuff is very challenging. I want to make that very clear. One thing I don't like, which I'm going to do videos on stuff other than machine learning, by the way, a lot of stuff. And just my learnings over the years of how to learn and being in these different spaces like martial arts and grad school. And one thing I want to say is this stuff is hard. I really dislike the people that are just like, oh yeah, I woke up and just aced the test. Like, man, fuck that, man. Understanding this shit is really hard. And everything is easy once you get it, right? Like everything's easy once you're good at it. Like, yeah, an armbar is fucking easy when you can do it. You're like, oh yeah, that's easy. Yeah, no shit, right? But like learning machine learning is very challenging and requires a lot of different fields. You have to be good at calculus, probabilities and statistics, Bayesian statistics. You have to be good at linear algebra. You have to be good at coding, object-oriented programming. You have to be good at so many different things. And, you know, that's why, you know, yeah, that's why that's why you get paid the big bucks, hopefully. If not, we need to work on how to get paid the big bucks. Because we know too much and we do too much and we practice too much and we add too much value to be getting paid, 180,000 a year or whatever. It's like, man, dude, the amount of stuff that I know to be able to make this stuff work in this way, I don't care what your market value says. Like, I want to get paid a compensatory amount, But anyways, this stuff is hard, guys, and it took me a long time to learn it, and I practice a lot. So I'm just gonna sort of gloss over that for now, but expect me to do an entire video on my learning progression and my philosophies on this. So, anyways, let's stop here for now. I'm gonna check this in, clean up the repo. I still need to edit videos and post things, but it's my third video done. Very pleased with this. Yeah. Later, y'all. Like and subscribe. Add comments. Please tell me where I need to improve, what you would like to see. I know that this can be a little confusing without the iPad, but once I draw this stuff out, I promise you it'll be a lot more clear. Anyways, I'm going to go eat. Good night, y'all.